Now we're going to delve a little bit deeper into sets and talk about subsets. Set A is a subset of set B if every element in set A is also an element in set B. So basically, set A is a subset if it's contained in set B. And we use this symbol right there for subset. Notice it's a different symbol than element. So with elements, which we learned about in the last few videos, you have a particular item is part of a set. Here we're saying that there's one whole set that is part of another whole set. So as one set is contained in another set. For instance, if set A represents all Americans who have tattoos, and set B represents those Americans between the ages of 25 and 29 who have tattoos, set B is a subset of set A. And you can look on page 64 as well to see more numbers there. So we're saying that set A is all Americans who have tattoos. Set B are just those Americans with tattoos who are between 25 and 29, right? So set B is part of set A. It's contained in it. So it is a subset. We could write B is a subset of A. Now this notation here means not. So it would mean not a subset. So for instance, if A is 1, 2, and 3, and B is 1 and 2, then A is not a subset of B, right? Because A are the values 1, 2, and 3, and B are the values 1 and 2. So these are not all contained in B, right? 3 is not part of B. So A is not a subset of B. But in this case, B is a subset of A, right? So if I change the ordering, the numbers 1 and 2 are contained in the set 1, 2, and 3, right? So you want to be careful of your ordering as well. It's really important that you're thinking of it the right way. So we're going to write is a subset or is not a subset in each blank to form a true statement. So is a subset, is not a subset. All right. So A is the set of numbers 1, 3, 5, and 7. B is a set of numbers 1, 3, 5, 7, 9, 11. So is A contained in B? Well, let's check. Is 1 in B? Yes. Is 3 in B? Yes. Is 5 in B? Yes. And is 7 in B? Yes. So all of A is contained in all of B. So A is a subset of B. A is the set X such that X is a letter in the word proof. Now, what that means for the set, if I write it in roster notation instead, it's P, R, O, F. Now, we don't have to write the O twice, right? We don't have to repeat. So the letters in the word proof are P, R, O, and F. B is a set of Y values such that Y is a letter in the word roof. So using roster notation, we have R, again, O, and F. So I'm just using roster notation to make this a little easier to see. So we want to know, is A set or a subset, excuse me, of B? So let's see, are they all there? Remember, this is A. This is B. So R is there, O is there, and F is there, but A contains P, and that's not in B. So this is not a subset. Right? You actually could do the other way around. It doesn't always work out that way, but B actually is a subset of A, right? Because all the elements of B are contained in A. So B would be a subset of A here, but A is not a subset of B. It has extra elements that are not in B. All right, A such that X is a planet of Earth's solar system, and B such that it's a set Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So we're trying to figure out here, are these actually sets, or I mean, are these actually subsets of each other? Now, I know there's always been some debate about Pluto, but we're going to go with the idea that Pluto is not a planet. So A is contained in B here, right? If A is a planet of Earth's solar system, while the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Those are all the planets. So everything is accounted for. A is a subset of B, and actually, we can even go further and say that A and B are actually equal, right? They contain the same exact elements here. So to be a subset, you could also be equal. And it's almost like you have a little equal sign right here, right? So you have that little line. It kind of reminds you that you could be equal here as well. There is something called a proper subset where we don't include this equality idea. So we know that every subset is a subset of itself. So for instance, A is a subset of A, right? So if all the elements are accounted for, it's a subset. But that allows things to be equal, which we just saw in the last example. So if we want something to be proper and not include equality, we use this symbol instead. It's sort of like the idea with less than and equal to, or just less than. So when we have less than or equal to, we include that equality possibility. Whereas if we have strict less than, we're looking at something smaller. And it's the same idea here. When we use this, this is not equal. So something has to be a true subset. It cannot be equal. Whereas if we use this notation with that little kind of equal sign underneath, it means that the two sets are subsets, or they could also be equal, and either way is fine. So that would be a proper subset. So we use it such that A is a subset of B, but again, they're not equal. So they're not actually the same sets. They would be different sets, and one is a true proper subset of the other. So we're going to answer, is it a proper subset, a regular subset, or both? Which symbol could we use? So A, X is a person, and X lives in San Francisco. B, X is a person, and X lives in California. So first of all, A is definitely a subset of B, right? So if someone lives in San Francisco, they do live in California, but obviously there are more places that you could live in California besides San Francisco. So A is a subset of B. And actually, A is a proper subset of B because there would be extra elements in B, right? Because people can live in more than one place in San Francisco, so there could be extra elements here. So really both is the answer for this one. So everything in A is included in B, and they're not equal. So I could use this notation, I could use this notation to make a stronger statement that they're not equal sets. So both notations would work here. For our second example, we have the set 2, 4, 6, and 8, and 2, 8, 4, and 6. Now, order doesn't matter for sets. And if you look, these are actually equal sets, right? So the elements in A are exactly equal to the elements in B. So the notation we could use here, if I want to use subset notation, is I could use this one, because this one allows for equality as well. So again, it's like the idea of less than versus less than or equal to. So because these sets are equal, technically one is still a subset of the other. So we could use this notation, but really they're equal. So let's talk more about subsets and the empty set. So we know what the empty set is, right? There's a set with no elements. So the empty set is actually a subset of every set, right? Because you can always have no elements as part of something with elements. It's kind of a weird idea to think of it that way, but the empty set is a subset of every single set. And it's a proper subset of every set except for itself. So for instance, what we can say is that the empty set is a subset of any single set in the world. It doesn't matter because there are no elements here. So if there are no elements, we can contain it in anything we want. And it's actually proper as long as B is also not the empty set, right? Because then they would be equal. Now, the number of subsets given a set. So basically this says like how many combinations could we make for different subsets with the elements given. So let's say that something contains n elements. How many distinct subsets could we form? And let's just try some examples with something with 0, 1, 2, and 3 elements, and then see if we can find a pattern here. Okay. So first we're going to start with the empty set or the null set. Now there are 0 elements there. The only set that we can make from the empty set is the empty set itself, right? That's it. Like, I mean, I can't put any elements in there. So there is only one subset here. Let's say I have a set with one element in it. So I'm using A here for my element, but you could use a number. Like, let's say it's the set with just the number 3, right? I actually could make 2 different subsets. So I could make what it is, right? That's set A, but the empty set is always a subset of all the other sets. So we could have the empty set as well. So I get 2 subsets. Now, remember here, when we're talking about subsets, we're saying that one thing is contained in another. So what's going on for the first example, we're saying that, let's use a different color here, that the empty set is a subset of the empty set. It looks kind of weird, but yeah, no elements can be a subset of no elements, right? They're all contained there. What we're saying here is that the empty set is a subset of A, and the set of A is also a subset of A, right? So each of these things here are a subset of the larger set. They're contained in the larger set. Now let's say I have 2 elements. And again, I'm using letters, but if it makes you more comfortable, you could use like 2 different numbers and try it that way. So let's think about all of our distinct subsets. Well, I could have the original set. I could have the set with just A. I could have the set with just B, or I could have the empty set. So you're looking at all different combinations that you could get from those 2 elements. And here I have 4 combinations. So again, what we're saying is that this set is a subset of the original, right? Everything here is contained in here. This set is a subset of the original. This set is a subset of the original. And then the empty set is a subset of the original. Okay, so all of these sets are contained in the original set. So there's 4 different combinations I can make from that original set. And in the last case, we have 3 elements. So let's see the sets that we can make there. And I'm actually just going to write it over here. I think it'll be easier to see. So the first thing I could do is I can always take the original set. Okay, so the original set is contained in the original set. I can also take each of the elements individually, right? Because all of those are contained in the original set. The empty set is always a subset of everything. So I'm going to include the empty set. And then I also can do combinations of 2 different elements. So I could do the combination of A and B is a subset of the original. The combination of A and C is a subset of the original. And then the combination of B and C is also a subset of the original. So I have 1, 2, 3, 4, 5, 6, 7, 8 different subsets that I can make here from 3 elements. So you're looking at all the different combinations and ways that you can break down a set. Notice that we're talking subsets here, not just elements. So that's why I'm always using that squiggly bracket, because that means set. So if I'm using this symbol, I'm talking about sets. So I need to use those squiggly brackets around it, not just talking about individual elements, but the whole set themselves. Now, if you can see the pattern here, I'm not sure if you can, but notice that each of these is really a factor with 2. So if I use exponents here, if I take that base of 2, because I can see kind of a doubling, 1 times 2, 2 times 2 is 4, 4 times 2 is 8, I see this base of 2. Well, 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power is 8. So we have the 2 following formulas that are going to be really helpful. And it says that the number of distinct subsets of a set with n elements is 2 to the nth power. So if you have 2 elements in your set, then you do 2 squared. If you have 3 elements in your set, you do 2 to the third. And that tells you how many different combinations of subsets you could get there. Now, when we're doing subsets, we also include the original set itself. So if you want to be a proper subset, so not equal, right? We're not including equality, then it's the same calculation, but you subtract 1 out. So we eliminate this option here. Find the number of distinct subsets and the number of distinct proper sets for each set. So my first set is A, B, C, D, and E. So I'm just going to call this set A. The cardinality there is 5. So the number of subsets is equal to 2 to the 5th power. Now you can use your calculator or you can multiply it out. You're doing 2 times 2 times 2 times 2 times 2. So you're going to get 32. Now the number of proper subsets will be that 32 minus 1. So you'll have 31 proper subsets. So that's all the different ways that we can rearrange those 5 elements to get subsets of the original set. All right, for this one here, I see my set is, I'm going to call this one B, X, such that X is a natural number and it's between 9 and 15, and 9 and 15 are included. So how many elements do I have? So let's see. I have 9, 10, 11, 12, 13, 14, 15. So I have 7 elements. So the number of subsets I could make there would be 2 to the 7th power. So if we're using our calculator, I'm going to hit 2, and then usually there's some sort of exponent key. So on some calculators, it is a little up arrow here. So I can use that and hit 7. And that will do my exponent for me. So it's 128. If you don't have a little up key, so again, your calculator, usually your exponent key looks like this, or it may look like this, like x to the y or y to the x, something like that. So that's what your exponent key would look like. So there are 128 subsets here. And for proper subsets, if we don't include equality, we get 128 minus 1, so 127. And again, those subsets are all the combination of different sets you can make that are still contained in the original set. Now, the number of subsets for infinite sets, so notice we've been talking about finite sets here, right, who have a distinct number of elements. Infinite sets are an interesting group when we talk about cardinality. And like I said before, if you're interested to learn more, I encourage you to read pages 69 to 70 about infinite sets to see how intricate of a concept infinity and cardinality can be. It's quite interesting and very unique because we actually have ways to sort of count infinite sets and see which sets are bigger or contained in others. So cardinality and subsets are sort of a similar but different idea. But on one idea, just to kind of do one example here of infinite sets. So let's say I have my natural numbers as my first infinite set. 1, 2, 3, 4, 5, etc. Now, another set I could have, one we see often is a set of real numbers, and we usually write it like this. So it's a bold R. And your real numbers contain all sorts of numbers. So not only do they contain the natural numbers, they contain 0, they contain the negative numbers, they contain fractions. So I'm not going to list everything out here. I'm just going to make a note here. They contain fractions and they contain decimals. So that there's a, infinite number of things that it contains there. This is not really good set notation, just kind of giving you a quick idea of what it contains. So this is something where the set of natural numbers is actually a subset of the real numbers. So we have two infinite sets and one is contained in the other. It's kind of an interesting idea because it's like, well, they're both infinite. How does this really work? They're both infinite. How do the real numbers have more than the natural numbers? It's a tough concept. So again, if you're interested, check out your text, but do know that we can have infinite subsets as well. The natural numbers are contained in the real numbers, for instance, or the natural numbers are contained in the whole numbers, right? So my natural numbers are contained in the set that's 0, 1, 2, 3, 4, and so on, right? So we can still have subsets with infinite numbers, which is sort of an interesting idea.